Okay, so we told you that there were three ways that plates could move. They could move towards one another, they could move apart from one another, and they could slide side by side each other. And that's these three words right here. Okay? Convergent, plate boundary. Converging, coming together. Divergent. Sorry if the mouse is moving a whole lot on your side of things. It disappears from my screen and I have to wiggle it to make it appear. So I apologize if it looks like I'm just doodling with the mouse. I'm actually trying to get it to show up. Alright, divergent plate boundary. Diverge means to move apart. And transform, the last one here, that's the sliding side by side one another. So convergent, divergent, not really new words for you. You probably don't use them a whole lot, but you know what they mean. Okay? So all you really need to remember here is that transform is the sliding side by side. Okay, but I told you that it depended on the rock type, the lithosphere type, as to what's actually going on here. So for converging plates, plates coming together, we currently have that occurring three ways. All right, we've got continental to ocean convergence. And again, this is lithosphere, okay? Crust, if you want to call it that, but technically it's lithosphere. Okay, continental lithosphere to oceanic lithosphere, oceanic to oceanic, and continental to continental. So in other words, we have two continents bumping into one another. That does something. We have two oceanic plates bumping into one another. That does something different. And we have areas where continental and oceanic plates are bumping into each other, and those do something even different again. So, first things first, continent to ocean convergence. So a continental plate bumping into an oceanic plate. That has a special name called a subduction zone. Subduction zone. You may recall subduction zones from volcanoes conversation. Subduct, subdued. One of them is going to lose this battle. Two things smashing into one another, one of them loses. And you might be thinking, I remember him telling me that the continents are lighter than the ocean floor. I bet they lose the battle if a semi-truck runs into a pickup truck. Who do you think's going to win? Yeah, not quite in this case. It's actually the oceanic crust that loses, probably because it's sort of on the bottom already. You follow me there? All right. When continental crust smashes into oceanic crust, the oceanic crust gets subducted, gets pushed down into the earth. It loses. And when it does that, it remelts, okay? And we could pretty much call that losing. Just reflecting back to volcanoes for a moment, all right, we gave this as the cause for many volcanoes to happen. The Cascade Range, west coast of North America in particular, is a great example of this. The Pacific plate is being subducted underneath the North American plate. So not only is that plate going down and melting and putting a whole bunch of extra magma there close to the surface, but do you remember what else is going down with it? Or even just think about what else is going down with it? All that ocean water, right? And water and magma, they don't really mix. It's kind of like oil and water. You don't try to put out an oil fire, a grease fire with water, right? Because it splatters and smacks and all over. It's a big mess. Well, that's exactly what happens, except deep down in the crust. And that bubbles back up through, works its way all the way through, believe it or not, up through the continental crust there, and we get that line of volcanoes that sort of mirrors the plate boundary. It's a good bit inland, but it is still a function of that. All right, so continent to ocean coming together is called a subduction zone. Continent wins, ocean loses, we get volcanoes. A lot of stuff there. All right, remember it all, please. Ocean to ocean, much simpler. Ocean to ocean, they both lose. Again, way down at the bottom, weight of the water on top of it. however you want to think about it. When two oceanic plates come together, and I always do this in front of the class with my hands. I'll make my hands like lay flat and then have my fingertips bump into one another. In this case, they both go down, pointing towards your lap. And we get something called a trench. All right, again, a word you guys know. You're familiar with the word trench. So when two oceanic plates come together, we form something called a trench. Famous trench is the Marianas Trench, the deepest place on the Earth. Okay. Trenches are also responsible for volcanoes. These are a special kind of volcano called island arc, and basically it's a chain of volcanoes that mirrors the plate boundary again. The difference being in this case is that it's usually right on top of the plate boundary. Okay, it's much closer to the boundary than we had with the subduction zone 1. Going back, if I've got you using your hands now, let's talk about subduction for a minute here, and take your two hands and again doink your fingers into one another here. And this time, instead of making both sets of fingers go down towards your lap to simulate the trenches forming, only have one set of fingers go down. Okay, and I'm doing this as I'm talking to you. My neighbors are probably like, what is he doing on his porch playing with his hands like that? If you have your fingers come together and slide one set down underneath, and then wiggle your fingertips. You see where they are? See how they're way under your knuckles, basically where your fingers leave the palm of your hand. All right, that's why those volcanoes are so far inland, because it's got to get down that far to melt and then bubble back up. Now you could stick your fingers through your other fingers, so they're sticking up like pointy volcanoes right now. All right, see, lots of fun you could have here. So anyhow, so with subduction zones, your volcanoes are a good bit off of the plate boundary. Okay, but with trenches, they pretty much mirror right on top of the plate boundary. We get the island arc volcanoes, Aleutian Islands. If you're wondering what the hell that word is there, it's the Aleutians. That's off the coast of Alaska. There, it kind of arcs over to Russia. Okay, it's a string of islands across the northern Pacific. Well, there we go. So here's our trenches. Okay. Here's Mariana. We talked about it's over here. One of these days, I'm going to get really snazzy with some program that'll let me make this image, the plate boundary image, make them one of them transparent, start stacking them, so you could kind of see how this all lines up. For now, you just have to unfortunately use your memory. So here's the Aleutian Islands are up here. Okay, not the land bridge. The land bridge was even further up. If you remember that from one of your history classes. But the Aleutian Islands down here, all the way down here. Remember, this is the Pacific, the rim of the Pacific plate. There's a smaller plate over here. I'm sorry, over here. It's just a mess all along. Again, if you've had the volcano chapter already, we talk about the ring of fire. Okay, here's why. Okay, back to plate movement. Continent to continent, they both win. Everybody's a winner. Using your finger analogy again here, when your fingers smoosh together and they're both continents, well, they go up, kind of like you're praying. Okay, continent to continent, almost said subduction. Continent to continent, plates moving together will give you mountain chains. We've got a few famous examples of that. The Himalayas, I alluded to earlier, with India joining Asia. This is the quickest, steepest, quickest forming, steepest, most active mountain chain right now in the world. The Himalayas are still growing. We've got the Appalachians, which are one of the oldest. Okay, if you've been lucky enough here in America to see both the Appalachians and the Rockies, you'd be like, no comparison, right? Well, the Appalachians used to look like that. They're just so incredibly old. Okay. Um, Remember the picture we showed you of Pangea? Okay. Um, they formed when Pangea formed. Okay. So they're well over 200 million years old. They've had plenty of time for weathering and erosion, plenty of time to be erased down to, and they're still pretty. Don't get me wrong. Those of you that haven't seen the Rockies, I'm not insulting the Appalachians by any means. The Adirondacks, as you guys call them up here, but just it's immensely different, immensely different. Yeah, so we've got some pretty famous stuff. And I forget if I said it or not, but those were formed when Pangea was coming together, when North America smooshed into what we call Europe right now. When Pangea was forming, that mountain chain came to be. So very old, very old. Divergence. All right, pulling apart. Luckily for you, there's only two types of divergent plate boundaries. Ocean to ocean and continent to continent. We do not have, what that implies is that at the moment, we do not have an area where ocean and continent divergence is happening. We don't have an oceanic plate pulling away from a continental plate. Okay? All right, ocean to ocean forms ridges. Ridges are another word for mountains. So where two oceanic plates are pulling apart, how the heck do you get a mountain chain, right? Probably what you're wondering, what you should be wondering, at any rate. What actually happens is that because the oceanic crust is so thin, because it's that close to the mantle, as it were, magma comes right up and fills into there, and you get a chain of mountains. The Mid-Atlantic Ridge, which I'm sure you'll see a picture of momentarily here, or at least an image on a map, is one of the tallest, longest mountain chains that there is on the planet. It runs all along practically from the North Pole to the South Pole, right down the middle of the Atlantic Ocean. Okay, that's a spreading center there. That's a word we use. Spreading center there. Don't tell the airlines, okay, but technically every day North America and Europe, South America and Africa as well, are spreading farther and farther apart, okay? So in the place there where those two continents are moving apart, okay, where the giant rip in the ocean floor there, new rock is being made every moment of every day, and it's more or less manifesting itself as a mountain chain. When two continents pull apart, we get exactly what you'd think. A rift. Like, what the heck's a rift? A tear, an opening, hey, let's call it a valley. All right? Sort of funny story about that I will save until the next opening here. Alrighty, so right around the summer before your senior year in geology, you go to what they call field camp, okay? And they basically take you out and they immerse you in geology. Growing up in the Midwest, as I did, we don't have any geology there. Well, we do, but it's glacial. It's all sedimentary, and it's a lot of green grass, and you can't see anything. They send you out west to see that Wile E. Coyote and Roadrunner looking stuff. And so anyhow, we get sent out there, and one day the teacher said, okay, we're going to go see a rift system, okay, where the earth is being torn apart. We're like, oh, cool, yeah. And so we're driving, and we get out, and I don't know what we expected to see. not necessarily the gates of hell opening up or anything like that, but, you know, something kind of dramatic. We're standing there on a bridge, an overpass kind of thing, and he goes, "See, look, isn't it amazing?" We're like, "What? The ditch?" Like, "Yeah, it's a valley. It's a rift valley." And I guess if we probably hadn't been 3 weeks into field camp already and pretty much just toast, it might have been cooler, and maybe to some of the kids it was, but it looked like a valley, okay? There may have even been a stream flowing through the middle of it. It wasn't too horribly deep or anything like that, but deep down inside, the cool factor, I suppose, was that one hunk of plate was ending, and another hunk of plate was starting. Yeah, well, we weren't impressed either, but we should have been, damn it. And if you're actually paying attention here and wondering, you say, "Wait a minute, I don't remember a plate boundary out in the middle of the, you know, Utah or Nevada or wherever you were." You're absolutely right. There's old suture lines all through here. These continents were cobbled together piece by piece by piece, and remember I told you there's exceptions to like the earthquake rule and whatnot. That's some of these old suture lines from way back when. One of the worst earthquakes North America ever had was on the New Madrid Fault, which runs from Ohio down to Missouri. And the earthquake itself was in Missouri. And, it was horrible, horrible, but nowhere near a plate boundary, but it was one of these suture lines. And when you hear about earthquakes in New York State, again, it's these old lines. So anyhow, going back, I think we were in probably southern Colorado or northern New Mexico at this point. And one of these old suture lines. And I don't even know, maybe it wasn't an active rift anymore. But, yeah. So, anyhow, rift system. Okay, continent to continent tears apart, and you get a valley, exactly what you'd expect. Ocean to ocean, maybe not what you'd expect. The ocean floors rip open, and magma pours out and makes a mountain chain. That's the ridge. All right, here's a map I alluded to. Here's your mid-Atlantic ridge. Occasionally it pokes out of the water. Okay, you see Iceland up here. Iceland is a giant volcano, the entire island. And it started at the ocean floor, grew all the way up. There's more chains here. Canary Islands. There's, military folks usually know it. Stopping point for fueling in the mid-Atlantic. I want to say it's the Azores or something. Map's kind of off here, looking like at any rate. But halfway between North America and Europe is a chunk of islands that stick up. They're part of the Mid-Atlantic Ridge as well. You got the Canary Islands down here. I think I mentioned those. And there's probably many others that we just don't know the names of. You have an East Pacific rise, the same idea over here. Okay, so we've got these giant ridge systems. And I talked about World War II. We started mapping the ocean floor. Warfare turned to under the ocean at that point, as an addition to on land and on top of the sea. So we needed to learn about all the nooks and crannies of the ocean floor. And then scientists in the 60s went out with their little yellow submarines, Alvin and whatnot, and really started poking around thanks to the data that they started the groundwork for back with World War II. And we really started to figure this out. And there's my mouse. So what we're going to see very soon here is we're gonna reference these ridge systems. We're going to reference the trench systems, and we're going to explain how everything is moving from ridge to trench. All right, kind of like a conveyor belt when you put your tray on after lunch, and it just takes it away to get, well, whatever happens to those trays when they disappear, right? So we're basically going to set up this conveyor belt system as we move from one plate boundary to another. It's neat stuff. Neat stuff. But we got one left. One plate boundary type left to talk about, and that is a transform plate boundary. Remember, transform is sliding side by side. All right. We're only going to talk about, pardon me, my phone is ringing for some reason. So we're only going to worry about one situation here, continent to continent sliding side by side one another. This is what's responsible for the majority of our earthquakes. All right. We have the San Andreas Fault referenced here. If you're not familiar with San Andreas Fault, that is the one running through California. Let's see that picture here. I do not. It's the one running through California. If you remember, over on the west coast of North America, we told you that the North American plate ends, the Pacific coast picks up, right? And we talked about the subduction zone over there, and that's all still true. The problem is, or the difference is that when you get right around San Francisco, the Pacific plate comes inland a bit. And everything south, well, not everything, but south of San Francisco, all the way down into Baja California there, the little tail that sticks out down there, that's attached to the Pacific plate. North of San Francisco, north of the San Andreas Fault there, is attached to the North American plate. And they're moving in opposite directions. Well, different directions at any rate. And in that case, what used to be pushing together of plates and the ocean losing, subduction, remember that? Okay. What it turns into down there is the Pacific and the North American sliding side by side one another. And now I don't want you to make your fingers bump into one another, but I want you to rub your knuckles from one hand against the knuckles from your other hand, and you get that little bub feeling, right? Here's the hard part to believe, that after these millions and millions of years that they've been rubbing knuckles, it's still not worn smooth. Okay? And unfortunately, because it still hasn't worn smooth, they can lock up. We'll talk about this when we get to earthquakes, but what happens is as they're sliding side by side and they lock up, they're storing energy, they're holding energy. And just like if you manage to lock up your knuckles, at some point, if you push hard enough, they're going to slip and pop, right? That's your earthquake. So that's why we get earthquakes over there. That's why we get earthquakes in a lot of portions of the world. Okay, it's this side-by-side, this transform movement. And as I started to allude to a little while ago, you get these all over the place. I'm only bothering you with one, okay? What we could arguably call the most important one for you to remember. So continent to continent transform. It's sliding side-by-side. It gives us earthquakes. And a really great example of that is over at the San Andreas area. All right, so let me check real quick, see how many slides I have left here as to whether or not we're going to cut a new, yeah, it's this last slide, that's what I thought. Whether we're going to have to cut a new, another segment of video here, but I'll just let this one run. We're only 10 minutes in. So, all of that aside, what actually is plate tectonics? All right. I usually draw this on the board. I see now that could really do with another slide or two, apparently. All right, so here's the idea. Their idea is called mantle convection theory. And mantle convection theory is based on the idea of, well, convection here. What is convection? Convection is why the weather works. Convection is why your upstairs of your house is super, super, super hot in the summer and the basement of your house isn't. It's related to density of things based on their temperature. Okay? Warm things expand. cold things contract, warm things rise, cold things sink. All right? And again, you knew much of that already. These are kind of in the wrong order here. It would make much more sense to say that, right? I'm going to pause this and actually look for an image to insert here. Give me a minute. Alrighty, folks. Thank you for your patience. Yeah, I know it didn't take any time on your side, but that was 15 minutes of me looking for pictures. So, mantle convection theory, temperature, density. Hot rock from the lower mantle rises, cool rock from the upper mantle sinks. It's at this point that I usually start talking about lava lamps and drawing these cool little pictures on the board. So that's where I found myself at a loss. If I sometimes talk kind of slow when I'm talking to you guys, that's because I'm thinking ahead to the next couple sentences that I want to say to you. And every so often I get hung up on something, and I got hung up right there because I'm like, oh no, how am I going to do this? So, convection. All right. Again, usually you hear about it with air. Warm air rises, cold air sinks. All right. Same thing is true of liquids. All right. Even solids expand and contract. So, anyhow. In our first image here, we see a Bunsen burner warming up a beaker full of water. And if you could see this, all right, happening, you would note that the water, as it gets warmed, rises up. And then, as it cools off, it actually sinks back down. And this warming and cooling makes what they call a cell, okay, or a current. In this case, it's a current, but the whole image here is a cell, or the area outlined by the current would be called a cell. Same thing on the other side here. And yeah, you can see bubbles welling up, but you don't see the water coming back down. And it's important here that we kind of have this visual image going on here, because well, soon enough I'm going to ask you to picture them as wheels on a conveyor belt. Okay? Alright, so anyhow, lava lamps. Same thing is going on with a lava lamp. Lava lamp is actually a grand physics experiment. If you think about a lava lamp on moment one, you got a big sort of hockey puck full of gunk down there on the bottom, right? And as you turn it on, well, where's your heat source? You don't have a Bunsen burner in there. You've got a good old-fashioned incandescent light bulb, right? That light bulb creates heat. That heat warms up this goo. Well, here's where the science comes in. This goo has a different sort of melting point, if you would, different capacity for heat than the liquid surrounding it. All right. So it warms up. It starts to melt. And as it melts, it expands a little bit. And as you know, it blobs up towards the top. And then what happens? Well, after a few moments, right, those blobs come back down, and you get this beautiful little ballet going on inside your lava lamp. Well, that only lasts for so long. If you leave these things on too long, what happens, right? Everything goes up to the top. You've totally messed up the temperature gradient that was inside of here. All right. There is no longer warm rising and cold sinking, because that light bulb has heated everything up, not just the goo, but the, well, we'll call it water around it. All right, and everything is the same temperature. So that's how lava lamps work. All right, if you don't know what I'm talking about somehow, I guess I can't tell you to go to the stores, at least not right now. We got that whole COVID thing going on there. But next time you can get an opportunity to look at a working lava lamp. I typically say go to Spencer's and stare at the lava lamps for a little while. Go stare at a lava lamp. Ask your aunt or your uncle. Show you theirs. Usually somebody you know has got one stashed away somewhere. There's a couple in our basement. All right? All right. Oh yeah, we're actually talking about the Earth, not lava lamps. Same idea, though. Okay. I love this image in that it actually incorporates ridges and trenches into the mix here. It shows that the heat of the Earth is warming up your material in your mantle here, the magma, and as such, it's rising up. Okay, and as it's rising up, it's pulling the rock on top of it. It's making a little cell here. Remember that cell we were talking about, the current? That is a wheel on a conveyor belt. And that conveyor belt wheel is moving this plate in this direction. I usually draw much smaller convection cells to make it even look more like a conveyor belt. Okay, imagine several smaller convection cells within here. Same thing over here. All right, and those wheels on the conveyor belt move this asthenosphere along. Well, at some point it hits an obstacle, in this case, a plate that's moving in the opposite direction, and well, it loses, right? We talked about trench systems. This must be oceanic to oceanic here to get a trench. So, neat idea, huh? This is a spreading center. This is a word you'll see in the textbook. And we're making new crust here daily, every moment of every day practically. Some of the youngest rock on the world is found right here. And if you're wondering, you know, what's to all this that we're talking about, that we can actually get data. We go over here with our little yellow submarines and sample rock all along this or all along this. And we find that it gets older as we move in this direction or this direction. Okay? We could take dating samples and we actually see the rock get older as we move farther away from the ridges. And we see that it's very young at the ridges. So we can get data on this. Alright? Alright, so anyhow, it's this idea that that explains why, sorry for the truck noise, that explains why the plates are moving around on the surface of the Earth. Now, as I said, why, and this is just arbitrary here, this one happens to be moving at a different speed than this one. They're still working on that. Probably temperature related or something along those lines. Why this material moves in this direction and this material moves in that direction. They're still working on that. But they've got the basics of the idea down, and we've got our best people working on it, you know, all the time. You think it's a neat idea, you go out there and help them solve the problem, okay? There's many fields of science that are still in development, and this is definitely one of them. So anyhow, really just a I was going to say icebreaker, but that'd be too punny there. Really just the beginning of studying plate tectonics here. This can be and often is an entire semester-long course if you were going on through in geology. So yet again, I find myself saying, well, we could be spending 14 weeks talking about this, and we did it in an hour. All right. So if you're left with a lot of questions, unfortunately, that's why. As always, do please feel free to email me with questions. I'll do my best to address them. But plate tectonics is and will be, okay, as long as the heat is coming out of the center of the Earth, as long as we've got a molten mantle, it will be occurring. You look at Mars, Mars no longer, the moon no longer has plate tectonics going on, but they did. All right. They don't have much reason to believe, as I understand it at any rate, that Mars is no longer tectonically active. All right. The moon definitely, okay, has cooled all the way through, but I'm pretty sure Mars has cooled all the way through as well. So This affects all the planets at some point in their lives. All the terrestrial, all the rocky planets at any rate. So, all right, folks, have a good one.